So what I'm going to do now is just give you a brief overview of technologies and techniques that can be used for virtual private clusters. And I'm going to focus on the two technologies at the bottom. For lack of sufficient time to cover everything here, but just to give you an idea of what's available out there. I believe you had a presentation on Amazon infrastructure. Amazon sells a service called a virtual private cluster, virtual private cloud, and that allows you to create a virtual private network inside Amazon infrastructure and even extend it back to your enterprise so that you can do cloud bursting with resources on Amazon. OpenFlow is a specification, a standard, and there's hardware and software implementations of this standard that allow for you to program network devices through a so-called forwarding instruction set. Basically allows you to program a network to support virtual networks. In contrast to VLAN, which has a well-defined protocol, OpenFlow allows you to program the network in a standard way using this standard interface. OpenStack Quantum, this is one example of a open source cloud stack that has middleware now that's available to create virtual networks connecting virtual machines together to form virtual clusters. Although these technologies are mostly confined to a single data center, or perhaps extending from a private cloud to a commercial cloud, like in the case of VPC. The other two technologies at the bottom, ViNe and IPOP Group VPN, these are technologies that allow the other use case that I described earlier, the intercloud example, where you can have federation of cloud providers connected by virtual networks. ViNe is a high-performance user-level managed virtual network, and IPOP, which is short for IP over P2P, is a peer-to-peer self-organized virtual network. So let me talk a little bit about ViNe. This is one project that is led by University of Florida, Mauricio Tsugawa and Joseph Fortes, my colleagues at UF. And the focus here is on a virtual network that allows, again, a deployment across multiple administrative domains and offer full connectivity among the hosts that are bound to the virtual network, regardless of the presence of firewalls and nets in the physical infrastructure. So again, recovering connectivity is one of the main goals of having a virtual network. The organization of ViNe is inspired by the Internet organization itself. So you have routers that are controlled by the ViNe, that run the ViNe software, and they are used as gateways to connect to other ViNe routers and form an overlay that supports the network virtualization for packets that are routed within the virtual network. The routers themselves can be configured dynamically, and there's a manager piece of software that can assist in the process of configuring these routers dynamically. So the picture here showing the ViNe architecture is similar to the picture that I showed earlier, where you have physical network and perhaps constrained by firewalls. And on top of this, you instantiate virtual machines, or it could even be physical machines in this technology. But there's a component there, the virtual network, that makes these systems talk as if they were part of the same logical LAN. So ViNe can do this without requiring software to run on the end nodes, as long as you can have a virtual router on the broadcast domain that the node is connected to. And there's a ViNe management plane that is shown in this figure here that is responsible for configuring these virtual routers that are attached to each local area network. So here's one example of how ViNe can deal with connectivity issues. So let's say you have 3 sites connected, and one of them is limited in its connectivity, that the site on the top left cannot communicate with the site on the top right because of firewall constraints. But ViNe, the overlay that's created here, allows for messages to go through an intermediary, in this case, the machine in the bottom called the QVR. And from the perspective of the user of the virtual network on the sites on the top, it's as if they're connected directly, but messages flow through this intermediate. Through the management interface, you can configure this behavior, but again, from the perspective of applications and users, it's as if they are connected by a logical LAN. ViNe is a high-performance virtual network. Here's one summary of the performance of the ViNe router over gigabit Ethernet, and it achieves close to a gigabit line rate. And again, this is when you have messages that have to cross a virtual router. In many cases, you have messages within the virtual network that could be completely independent from the virtual router if they happen to communicate within the same local area network. There's no overhead induced by the virtual router. And again, this is user-level software implemented in a high-level language, Java. In terms of management, there's an architecture based on the ViNe central server. It takes requests from users and ViNe routers and configures the routers appropriately to respond to requests, for example, to create a new virtual network, or to add new resources to a virtual network, or to terminate a virtual network. So to illustrate one of the use cases of this virtual network, let me give you one example that was in cooperation between FutureGrid and Grid 5000. And in this example, the researchers were interested in this idea of running an application, a parallel application that uses Hadoop. This is a version of the BLAST sequencing application that runs on top of Hadoop. And in this example, they wanted to run this across resources on multiple sites. So the idea is to create a virtual cluster where you can run Hadoop, and then you can run this CloudBLAST on top of Hadoop. And this demonstrated that this was possible with 6 different sites, 3 FutureGrid, 3 Grid 5000 sites, one of them fully isolated from the internet and requiring the use of this virtual router in order to establish connectivity to FutureGrid. So this is how the topology looked like. Again, the ViNe topology was configured to enable the virtual machines running on all these different sites to behave as if they were part of the same local network. And a total of 750 VMs were deployed in this example, with a total of 1,500 cores, and BLAST was executed successfully using this Hadoop version and showing a very good speed up, and again, harnessing resources available from multiple providers.